Three, two, one. Alright, another pre-recorded video today. So here we're going to talk about matrix inverses. Last time we talked about matrix multiplication and matrices multiplying vectors. And with all that, we're primed and ready to talk about matrix inverses. Alright, so let's start off with, again, a bit of motivation here. So we now know that any system of linear equations, all of them look like this. They can be written as a matrix equation, where A is the coefficients, X is the unknowns that we're trying to solve for, and B is just the right-hand side. Alright, now obviously in this form here, we know A, we know B going into solving a system of linear equations, so we would like to algebraically manipulate this to isolate X. And as we noted, an obvious choice here would be to multiply A by something and get the identity, and that would then isolate X, but in order for that to be proper, well, we needed to prove matrix multiplication is associative, which we did. Alright, so like I just said, if I can find a matrix B, so that B times A is indeed the identity, then X can be solved for as follows. Well, X is equal to the identity times X. It's just the fact of the identity matrix. If we know that B times A is the identity, we can sub it in. You can then move the parentheses over, as we know matrix multiplication is associative, and by hypothesis A times X is B, and there we go, you've isolated X. Alright, great. So that's the plan. We want to be able to address the question of, given a matrix, can I find a matrix B so that multiplying B on the left of A gives me the identity, which would then let me solve for X. Alright, so note that this has some consequences about what type of matrix A could possibly even work in the first place. Right, this would say that the system AX equals B can always be solved, and not only can it always be solved, it can be solved uniquely. So if such a matrix B existed, the system always has a unique solution, and that means that every column would have to be a pivot column. Right, every column of A would have to be pivot, because I'd be able to solve every single possible system. There's no way that any one of those would fail to be pivot. Right, one of them failing to be pivot would ensure that I'd have not a inconsistent system per se, but a system that possibly has more than one answer, but the existence of that matrix B means that there has to be a unique answer. So because every column would have to be pivot to ensure that there are no free variables, note that we have to be in the situation where n is less than or equal to m, right? I need enough equations to cover the number of rows that I have, right? Because, right, if I can always solve Ax equals B, everything needs to be pivot. So that puts some restrictions on the sizing of the matrices here. And for reasons I'll become clear in a little bit here, we're only going to worry about the case when n is actually equal to m. So it turns out that when n is strictly less than m, there is still some theory you can do, but it's not quite as nice. So you get into these sort of like a left inverse versus right inverse sort of arguments, and it goes a little bit further than anything we need. But we'll just focus on the case of square matrices. Alright, so given a matrix A, we'll call a matrix B an inverse if precisely this equation holds. B times A is equal to the identity, what we're looking for, right? Because we want that to be able to solve Ax equals B. And what's quite shocking is that if B times A is equal to the identity, it turns out that the other matrix multiplication that you can then perform, now note because we are assuming everything is square, A times B and B times A are actually defined, but quite shockingly, if we know B times A is equal to the identity, then it's got to be that A times B is also the identity. Now, right, that's pretty alarming, or at least it should be, because we know matrix multiplication fails to be commutative, so the fact that I'm allowed to actually go, well, in this case, they actually are commutative, A times B and B times A are actually equal to the same thing, it's quite astounding. Alright, now why is this true? And here's where the squareness of everything is going to, again, come into play. Alright, well, since we know we have an inverse, that means Ax equals B will always have a unique solution. Right, because x is equal to b times b, capital B, lowercase b, that means that I can always solve ax equals the standard unit vectors. Right, so ax equals ek can always be solved, and specifically, we know that a times b times ek will have to equal ek. Right, so just replace b here with ek, and then that's what we get. But recall, multiplying by the standard unit vector gives you the column vector, and then a matrix times a column vector is really the column of the matrix multiplication. So, hey, every column of a times b are the standard unit vectors, meaning that a times b has to be the identity matrix. Hey, look at that. Pretty cool. Alright, it's pretty neat. Alright, so equipped with that knowledge, we now know that if you have an inverse, then not only is b times a equal to the identity, but a times b also must equal the identity. So that means we have both products equaling the identity, both possible products. And equipped with that, we can now prove that inverses indeed have to be unique. All right. So, if your matrix has two inverses, they have to be the same thing. So note we were being careful with our language here. We didn't say the inverse, we said a inverse. And we need to prove they're actually, right, there's only one if it exists. All right. So we'll prove b is actually equal to c, and this is an all-time classic proof, proving inverses are unique. Note the matrix B is equal to b times the identity. We know that if you have an inverse, it doesn't matter which side of the matrix that you multiply it on, you'll always get the identity. So the identity here turns into a times c. But by matrix multiplication being associative, I can move the parentheses over. I know b times a has to be the identity. Multiply by the identity gets us the original, and there we go. Inverses, when present, are unique. Cool. So I like this proof for a lot of reasons. I think this particular proposition highlights, right, the theoretical side of things of mathematics, and also really drives home like why you gotta do proofs. Because again, we built matrix multiplication wholesale. We created it from scratch, right? And you don't know what properties it has until you prove them. So you gotta actually work out the details and prove everything, right? And here we see, inverses. We want this property to hold because we want to solve equations like that. And from that property, we were able to prove this one by other facts of matrix multiplication. And then equipped with this knowledge, we're then able to use the associativity to help us prove inverses are, in fact, unique. Right? And again, this highlights, when you make a math definition, you want it to be as, like, weak as possible, right? Like, you don't want to say that, oh, B was the unique matrix with this property. Well, B is a matrix with this property. We don't know if it's unique or not going in. We can prove that. So, we're able to, right? So while this might feel a little pedantic, it kind of has a purpose, right? And again, highlighting the essential properties of algebraic operations, associativity, that we need to prove along the way. Alright, so since inverses are unique, we can give them a fancy symbol, and the one we'll use is a to the negative 1. Okay. Now, naturally, I would like to compute formulas for this, right? So given a matrix, if it has an inverse, I would like to know how to actually find a inverse. Well, in the proof here, we noted something, right? We noted that the columns of B are precisely the things so that when you multiply A by them, you get these standard unit vectors. So if you have an inverse, you know A times A inverse is equal to the identity. Well, taking the columns of both sides tells you that this has to be true. So the columns of A inverse can be found by simply solving the system for all possible standard unit vectors. So if you have an inverse, this has to have a solution. Furthermore, it has to have a unique solution. And we can solve this simultaneously, so you don't have to like set up one augmented matrix for each EK. You can set up an augmented matrix that on the right-hand side has all of the EKs, and then we can just go ahead and solve it. So for example, if I had this 3x3 matrix and I wanted to know if it was invertible or not, I augment all three things that I need to solve for, all E1, E2, E3, and then go for the solve, and then this first column is guaranteed to be the first column for A inverse, because that would correspond to solving if the right-hand side was equal to this. This is the second column of A inverse, because it would correspond to solving for that standard unit vector. And this last column is the last column of A inverse, because it would correspond to solving for the A sub 3. So this little ref computation that I did here reveals to me that this matrix is invertible, and its inverse is precisely that. So if you want to actually compute the inverse of a matrix, all you need to do is augment on the right by the identity matrix, and then perform a ref. And note that this will do a simultaneously solving all of these possible systems. So, once again, as noted, when it comes to linear algebra things, there's a lot of song and dance about a lot of stuff, but ultimately at the end of the day, you make this and you do a ref. So it pretty much ends up being what you do. All right, and note that this method can be used to detect when A fails to be invertible, because if you set up the right-hand side with the identity matrix and you ref it, and on the left you do not get the identity matrix, you get something like this, right, then this last column here would then correspond, right, so this last row here of all zeros, basically meaning that, well, yeah, you can't actually solve all of those systems. One of them is going to fall apart on you, and indeed we see here that, yeah, there's just, right, so whatever we get on the right here, it isn't actually particularly useful. It's basically junk, right? No, it says that there was no hope of actually solving any of those equations, or there was no hope of solving one of them. All right, cool. So note this reveals that our good friend 1, 2, 3, 4, 5, 6, 7, 8, 9, that 3x3 matrix fails to be invertible. And note that this whole process, if you're looking at it, you may note that, hey, wait a minute, this seems to be asking, hey, can my matrix be row reduced to the identity matrix? And indeed, that's literally what this is, because if you are invertible, AX equals those standard unit vectors has to be able to be solved, and the only way all of those could be solved is if you were row equivalent to the identity matrix, and as we already discussed, being row equivalent to the identity matrix for a square matrix is called being non-singular, and indeed, a matrix is invertible precisely if it's non-singular. Alright, so we can use the words non-singular and invertible interchangeably. I am not a fan of the phrase non-singular, as we already discussed, so I'll stick with calling these things invertible matrices. Also note that this is equivalent to the columns of our matrix being linearly independent. Right, again, we saw that was the equivalent fact for being non-singular, which again was the null space is trivial. So a lot of these words just mean a lot of the same things. Okay. All right, cool. So we now have necessary and sufficient conditions for a matrix to be invertible. We have a method for actually computing the inverse. Naturally, we would now like to address a couple of more things. So specifically, formulas. Right? Well, I can compute the inverse using a ref, but it'd be great if I had like an explicit formula for what the inverse was actually equal to. And for 2x2s, there's an incredibly famous formula for this. So if you have a 2x2 matrix, it is invertible precisely when AD minus BC is non-zero. And the formula for the inverse is the following. 1 over that magic number times swap the diagonal and negate the off diagonal. Okay, so that magic number, AD minus BC, you have almost surely encountered it in your math life at some point here. Now here it is officially. Later on in the semester, we will study this number because it's very special, and it exists for other matrices beyond the 2x2 case. We'll talk about that later on. We will determine it later. All right, and so this formula right here, so in your mind palace where you got the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a, go ahead and put this right next to it because this is probably just as important as that equation is. All right, so let's go ahead and prove that indeed a is invertible precisely when this number is non-zero, and the formula for the inverse is given as follows. All right, so what's the trick going to be? Well, the trick is we're just going to multiply the matrix A by this matrix right here. All right, so let B be that matrix, and let's look at B times A. Right, because again, to be the inverse, we need B times A to be the identity. And it just so happens that when you do B times A, you will pick up precisely this matrix right here, which, note, is a scalar multiple of the identity times the magic number. Hey, that's pretty magical. Alright, so obviously if the magic number is non-zero, we can divide it over and then get A times that matrix is equal to the identity, and thus B, that equation right there must indeed be the inverse for A. And so there we go, we've got our formula. Okay. Alright, now we want to prove that when AD minus BC is non-zero, then our matrix A fails to be invertible. Okay. Alright, so suppose that AD minus BC is equal to 0. Alright, well then B times A has to equal 0, because if this is 0, then we're scaling the identity by 0. Now if A was invertible, then I can multiply both sides of this equation by A inverse. That will isolate B, but then B would be equal to 0, which would mean A, B, C, and D are all equal to 0, which would force our original matrix A to equal 0. But then A can't possibly be row equivalent to the identity matrix, because it's a matrix of zeros, so you can't do any row operations to do anything. And that obviously contradicts my assumption that A was invertible to begin with. Alright, so it's got to be that A failed to be invertible, so there you go. You are invertible precisely when the magic number is non-zero, and when the magic number is non-zero, we have that formula for the inverse. Alright. So, a very famous formula, we now have it, and note that this allows for some slick computations for 2x2 systems. So suppose I wanted to solve x plus 2y is 2, 3 plus x plus 5y is equal to 7. Alright, well, break this down into the matrix equation ax equals b. Here our matrix A is 1, 2, 3, 5, our x is xy, and our b is 2, 7. Okay, well, this matrix A is indeed invertible in the magic number AD minus BC. So that'll be 1 times 5 minus 3 times 2, which is a negative 1. We swap the diagonal, negate the off diagonal, scale it by negative 1. The inverse of A is given by that. And as we know, if you have the inverse, then you can solve Ax equals B by setting x equal to A inverse times B. Alright, so that's what we do right here. So xy is equal to A inverse times the right-hand side B. So here you get a negative 10 plus 14 giving me a positive 4, and then a 6 minus 7 giving me a negative 1. And hey, there you go. Slick computation of the solution of a 2x2. There. Neat. So it's a pretty quick way to solve 2x2s by just using the inverse of a matrix. Pretty nice. Now, it's worth noting that solving 2x2s can be done with matrix inverses. You can solve 3x3s and beyond, but computationally speaking, it's a bit more like wasteful to just compute the inverse and solve for it. There are other more faster and efficient ways, but we know theoretically you can solve Ax equals B by multiplying both sides by A inverse now. Alright, for 2x2s, you can do a pretty slick computation for it. Alright, and let's wrap up our discussion of matrix inverses by proving a couple of formulas for matrix inversion. Okay, so if you have an invertible matrix, then its inverse is also invertible, and the inverse of the inverse is the original. And again, that shouldn't be too shocking. If you have a product of invertible matrices, then the product is also invertible, and its inverse is, note, not A inverse B inverse, but rather B inverse A inverse. And again, this is coming from matrix multiplication failing to be commutative. Right, the order in which we multiply does, in fact, matter. Even though it turns out for getting an inverse of a matrix, you only need to multiply on the left to get the identity to verify that what you have is indeed the inverse, because the other multiplication, A times B, is also equal to the identity. While we prove that for A times B to be invertible, we actually need the order to swap. Again, we need that anti-multiplicative thing to happen. Alright, so if you have an invertible matrix, its transpose is also invertible, and the inverse of the transpose is the transpose of the inverse. So again, our favorite phrase in mathematics, the x to the y is the y to the x. And then finally, scaling an invertible matrix by a non-zero scalar keeps you invertible, and the formula for the inverse is what you think it should be. Cool. All right, so note matrix multiplication, transposing, and scaling, some of our fundamental operations interacting with our notion of invertibility. Note summations are out the window, and generally speaking, the sum of two invertible matrices will almost surely not be invertible. Well, that's maybe not generally true, but A times B being invertible, there's no good formula for that, unfortunately. Right, it shouldn't be too shocking. We know that if you have x plus y, well, 1 over x plus y is not the same thing as 1 over x plus 1 over y, so why should that work for matrices? Alright, so let's go ahead and prove these 4 facts. So in order to verify that A inverse is invertible, I need to multiply something on its left to get the identity. Well, we know multiplying A inverse on the right gets you the identity, so this means that A has to be the inverse of A inverse. Alright. Alright, if I want to prove A times B is invertible and its inverse is this, multiply it on the left by this matrix right there. And here we see, right, the order matters because I need the A inverse times A to be the identity. The identity then goes away, and then I have B inverse times B giving me the identity, and thus B inverse A inverse is the inverse of A times B. Right, and then 3 and 4 are dispatched in a similar fashion. Missing a piece of my parenthesis right there. Let's go ahead and fix that. Alright, I want to prove that A transpose is invertible. Well, I can transpose the inverse, and I have a product of transposes, which is the transpose of the product in reverse order. But A times A inverse is the identity matrix, and transposing the identity matrix does nothing, because you swap the rows and the columns. Well, the rows and the columns are just the standard unit vectors, so swapping doesn't do anything. Alright, and hey, there we go. A inverse transpose is the inverse of A transpose. Alright, and then finally, A alpha A is invertible. Multiply on the left by this quantity right here. The scalars can be pulled out to the front. They'll multiply to 1. A inverse times A is equal to the identity. Scaling the identity by 1 just gives you the identity. And there you go. We've got that this is in fact the inverse of alpha A. And the proof is over. There we go. Pretty cool. Alright, so that's the story on matrix inverses. So that covers all the material that we need for our exam, which we will be taking on Friday. So good times. Alright, so I'll see you in person on Thursday, and we will review. It'll be a good time.